I will talk about the Otello survey. I want to thank you, European Pathala, and the organizers of this meeting. I'm José Antonio de Diego. I'm working in the Institute of Astronomy of the National Autonomous University of Mexico, and I'm an Otello's team member. Well, the talk is about the Otello surveys and the galaxy classification and redshift estimates using non-sequential neural networks. Well, the motivation of this work is that the size of available data is growing exponentially, and in the last 20 years, we have increased the number of data in 5 orders of magnitude, and even that the CERN, for example, has a larger budget that all the astronomy in the world, more or less we have the same trend of data as the CERN. So in astronomy, there have been a lot of surveys, and there are planned more surveys in the future. And these surveys are important because they are needed to explain the galaxy formation and evolution, the physical environment and environmental properties, and constraining cosmological models. These surveys have actually are more depth and are also using more observations. So we have a time domain astronomy, which tries to find variable objects and see the evolution of the different objects in astronomy. So the size is increasing, the size of the data. We cannot manage this data manually, and we need new tools to study this data. In particular, in extragalactic astronomy, we are interested in galaxy classification and redshifts. For galaxy classification, we have traditionally used the morphological classification or visual classification as the scans by Hubble and the binoculars. There have been several attempts to use automatic classification. The first were trying to fit the spectral energy distribution, and there are several software for this. And also machine learning using support vector machines and random forests, for example. And in the late times, using neural networks. Most of them for galaxy classification use image neural networks, but also tabulated data, as in the case of a single of our publication last year. The problem with the image data is that we need well-resolved images of galaxies, and this limits the range of redshifts and the size of the galaxies we can classify. Just to compare the neural networks with other automatic classification methods, well, in last year we published a paper with the Otello catalog also. We'll talk about it later. And we have here the results, the main results. This is the baseline. Baseline is a naive classification. It consists in assigning all the galaxies to the most populated group. In this case, we were dividing the galaxies in early type and late type. So as the most galaxies were late type, the accuracy of the classification of the baseline classification is very high. It's about 94%, because 94% of the galaxies were late type. Using the UMINUSR color by Strateva et al. In 2001, we get this classification using 100 bootstrap over the sample. Using linear discriminant analysis, we get a better estimates of the classification of the galaxies. But using one neural network, the classification is much better. You have here the numbers. It goes from the baseline, which is 94%, to the DNA, which is over 98%. About galaxy redshifts, the methods are more or less the same: set fitting, support vector machines, random forest. And there has been a lot of work in the late times using neural networks. I will talk a little about this. And well, you can see that the training data that we need for neural network training is about thousands, tens of thousands galaxies, even hundreds of thousand galaxies. Redshifts are usually low because it's hard to get spectra from galaxies to measure the redshift. So many of these works have worked with the Sloan Digital Sky Survey, with the Sloan. And usually the redshifts are very low, and so the errors are very low too. But when we go to samples which are over redshift 1, the errors increase about 1/10 of the redshift. Well, for this work, we use the Otello Survey. It was made with the instrument Osiris in the Gran Telescopio Canarias, which is a 10-meter telescope in La Palma, Canary Islands. And it's a deep emission line survey. Consists of observing with a narrowband filters with a bandwidth of 12 angstroms in an atmospheric window, which is about 9,200 angstroms, more or less. And the catalog of the Otello catalog also includes ancillary data from X-rays to infrared. So if we see the Otello spectroscopic redshift sample, the spectra of this sample was obtained with the Deep2 Galaxy Redshift Survey. We use the optical and the infrared photometry, and we see that the sample is very small. It's only 370 galaxies. Less than 10% are early type, and the rest are late type. And we see here more or less the distribution in the R band and spectrum. And we see that, well, most of galaxies are between 0.2 and 1.3. And we can see also that the peak of the magnitudes is about 24, 25, which means that this is a bright sample, because Otello's 50% completeness is about 26, magnitude 26.38. And what's the problem with these classifications? Well, usually different neural networks for classification and redshift. We use one neural network for one thing and one neural network for the other thing. And these neural networks are different even in type. Usually for classification, many people use images, and so they need neural networks based on ConvNets. While for others, for redshifts, it's necessary photometric data, and we use dense neural networks. And the problem is that there is a degeneracy in the colors of the galaxies. So a late type galaxy may have the same colors as an early type galaxy if the late type galaxy is at high redshift, and the early type galaxy is at low redshift. So for the colors, we may have some problems. The problem with using the different neural networks to classify and to estimate the redshift is that we can have non-consistent results. I mean, we can classify the galaxy as late type, but then measure the redshift as it was an early type. Usually, the neural networks used up to now are sequential neural networks, which means that they have a very simple topology. Layers are piled up, and you see that there is an input layer, several hidden layers, and then a single output. This kind of sequential neural networks cannot produce different outputs. So we need one sequential neural network for classification and another different for redshift estimates. What we have done here is to use a non-sequential neural network. And we see more or less here how it works. We have an input, which is the photometric data, some base calculations within the neural network, and then the output of this block of data of the network. The output passes to another part of the network, which is dedicated to classification, and to other part, which is dedicated to redshift. As classification is very good in early type and late type classes of galaxies, we use first the classification, and the output of the classification goes outside as an output and gives a probability this galaxy is an early type or late type. And these probabilities also fits the redshift block, which then uses the classification and the redshift and the photometric data after some previous work, and gives us an estimate of the redshift. Well, this is the results for our galaxy. We use a technique which is leave one out cross validation, which consists basically that for each element of the sample, we train with the rest of the elements and predict this element, and this 370 times in this case. No? The baseline accuracy that we can get assigning all the galaxies to the most populated class, which is the late type, is 92%. And with this classification, we get an accuracy of 98%. You see that we have a very low number of misclassified objects, only 3 early type galaxies and 3 late type galaxies. However, if we see to the rate of the true early type, to the rate of the true early type detections, rate of the false late type detections, rate of the false early type detections, and rate of the true late type detections, we see that the numbers are different. We see that the percentage of the true early type galaxies is 90% detected, but the number of the late type detected is 99%. And this is because the accuracy, which we can calculate it, depends on this parameter here, which is the prevalence class. As our prevalence class is very high, then the accuracy is biased towards the prevalent to this prevalent class. If we make a receiving operating characteristic curve, a ROP curve, we see that this classification corresponds to this point, to the cyan point. We see that, well, it's about 90% for the true late type galaxies, but for the early type galaxies, it's about 90%. It's about 90% only. We can think that we wish to be here, which is all the classification is perfect, but if we cannot be here, we want a classification that is the closest to this point, to the 1 point, perfect classification. Why? Because if the accuracy depends on the sample prevalence, it's a bad thing. If we change the sample, we change the accuracy of our estimates. To calculate this number, there are different ways. We use the Jordan's G statistics, which provides a well-balanced true early type and late type rates. And this J number is between 0 and 1. In this case, it's about 0.9. And with this number, in this case in particular, we get practically the same number for the rate type, rate through light type, and for the true early type rate, 96.8% for both, which is this point here. Then this is a classification that does not depend on the sample. This is the important point. If we compare the contingency tables, well, for the previous classification, which is the maximum accuracy, we got 98%, and we got very small number of errors. With the Jordan's, the number is larger, but the proportion is the same. It's about 10%, and no, it's about 1 in 30 and 11 in 328. No? Basically, the proportion is the same. But the accuracy is not longer 98%, but no, 97%. If we look, this is the probability scores yielded by our network. In pink, there are the early type galaxies, and in blue are the late type galaxies. If we zoom on this plot, we can interpret these numbers. This is the maximum accuracy, which is a probability score of 0.5, and the Jordan statistics, which is about 0.9. And these are the numbers. No? These are the 3 early type galaxies which are bad, are misclassified, and these are the 3 early type galaxies which are misclassified. But when we use the Jordan statistics, there is only 1 early type galaxy misclassified and 11 late type galaxies misclassified. Well, let's talk about the redshift. And this is the Otello photometric redshift with the Lefort templates, the fitting that they got. This is the spectral redshift. This is the photometric redshift. We see that the errors in this plot are dominated by catastrophic outliers. Here we have in red overplotted the neural network estimates, and we see that the dispersion of the neural network estimates is much lower than that of the Lefort templates. The slopes are basically the same. It's the perfect slope will be 1, and these are both 0.98. If we see to the residuals, we see that most of the residuals are shared, basically. The mean is 0, and the intercept point of the residuals, we'll see it later, it's more or less the same, and the slope of the residuals also are very similar. But the standard deviation, because the neural network gives a more exactly, more accurate results. And if we see the results here, the residuals here, we see that for templates, and this is for our network, comparing with the fits, and we see, well, they are very good, but there is some trend which we saw here in the slope, which is not exactly 0 in both cases. We see this slope here, and well, we have a hint that there are an overestimate of the redshifts at low redshift, and an underestimate of the values at higher redshifts. These results are similar with other people working with neural networks already obtained. This is the case of Singal et al. We see in this is the neural network fitting they got. We see this kind of sigmoidal shape, and this is the fit for the LEFAR templates, and we see these catastrophic outliers, more or less like our results too. And here we have the dark energy survey fit, and we see also this sigmoidal shape of the fit. So an important question is, why do neural networks fail near the borders of the distribution? And well, there are two things that we can argue to explain this. One is that the neural networks are approximation functions, very good for interpolation in a finite range of input data. And so as the data that we input is between 0 and 1.4, all the results that all the calculations that provides the neural network will be in this range. So if we have a galaxy here, for example, it will not provide us a result here, but the error will be towards lower redshifts. And the same for a low redshift galaxy. If the galaxy redshift is here, the network will not give us a result in this part below 0, but only in this part. So there is a movement of the predicted redshifts for low redshifts to higher values and higher redshifts to lower values. Moreover, the neural networks also tend to predict on the most populated range of the dependent variable. So if we have most of the galaxies are between 0.2 and 1.3, the neural network will tend to populate in its prediction this region. So for conclusions, we can use non-sequential neural networks to build consistent models for classification and redshift estimates. And for this classification, we should take into account the imbalanced nature of the galaxy samples. Usually you have much more late type galaxies than early type galaxies. Third, that neural networks redshifts are more robust and produce far fewer catastrophic errors than spectral energy distribution fitting. But the lack of a spectroscopic high redshift samples dampers the development of neural network redshift models. So future work is to build reliable artificial high redshift samples of galaxies for training. and include image capabilities in non-sequential neural networks. Thank you.